Jai Shri Gurudev, dear students, welcome to Module 5, which gives you a basic introduction to state space modeling and analysis. In the fourth module, we have discussed about different types of stability analysis, wherein we have discussed about stability analysis of the system in the frequency domain using polar plots and Nyquist plots, and you have learned how to analyze the system using the frequency plots, and also we have dealt about Brode's plots in the frequency domain, which helped us to determine the stability of the system in the frequency domain. So in today's session we will discuss about another important technique which is used for analyzing the systems, named as state space modeling. So this is considered to be one of the modern important technology which is used in most of the places. So coming to the lecture outline, in this module we will discuss about basic definitions, state equations, state diagram, controllability, observability and controllability of output. So basically in the earlier methods like Bode's plots, root locus, Nyquist are considered to be the classical or the conventional methods for the analysis of control system, whereas state space analysis is considered to be the modern method of control of system analysis. And modern control theory is contrasted with the conventional control theory in that most of these are applicable to multiple input multiple output systems, which may be linear or non-linear. Sometimes they may be time variant or time invariant, while later it's applicable only to linear time invariant system with single input and single output systems. So coming to the major advantages of state space analysis, it is applicable for multiple input, multiple output systems, and for linear, non-linear system, along with variant and time variant systems also. Initial conditions are included in the analysis in the state space. Digital computers can be used as analysis which is done in time domain, and it is also applicable to a group or a class of inputs. And the number of equations is equal to the order of the system here in state space, and it gives information about the complete behavior of the system. This is very crucial. The complete behavior of the system is can be analyzed using state space, and using vector matrix notation it is possible to write a state model in a compact form. And state variables are selected need to be physically measurable and observable. So these are the main advantage of state space analysis. Coming to definitions, the first definition what you have to know here is what do you mean by state. So state of a system is the minimum set of variables that are considered such that the knowledge of these variables at a particular time t0 together with the input for t greater than or equal to that particular time t0 will completely define the behavior of the system at any time for t greater than 0. That means if I know the variable at a particular time instant t0, and if input is given for but at that particular time, so the complete behavior of the system could be judged at any instant of time t greater than 0. So that is what we mean by state of the system. This is one important definition what we need to know. So state gives us the behavior of the system at any instant of time for any input. Coming to state variable, the state variables of a dynamic system, they are considered to be the small set of variables that determine the state of that particular dynamic system. So the variables which are used to determine the state of a system are considered to be the state variables. And state vector, if n variables are needed to completely describe the behavior of a dynamic system, then n variables can be considered as components of the vector x, and such vector is called as state vector. So the vector which is constructed from the components of the system are considered to be the state vector. And state space definition is given here. It is defined as the n-dimensional space in which the components of the state vector are represented in a coordinate axis. So these basic definitions should be remembered and they can be asked as a theory question also in the examination. So please make a note of it. So let us learn the definitions now with examples. So let us take two variables x1 and x2 which are considered to be the state variables that define the state of the system completely in two-dimensional space, where x1 is taken on x-axis and x2 is considered to be your y-axis variable. So somewhere I have represented a dot here indicating the state of a system at t equal to time t1. And if I join a line from the origin to this particular point, that is taken as the state vector along with the direction of the arrow giving you the direction of the vector. And the state space vehicle for this state space is given as x dx by dt. So here I have considered a state t equal to t1, and this is the velocity that we are going to consider for this particular state, since it is dx by dt, and this is considered to be the position with respect to time t and the variable x, and this is considered to be the state vector. Now coming to state equations, in state analysis we will consider three types of variables, that is input variable, output variable and state variable in defining a dynamic system. So we have two output equations, that is state equation and output equation. So state equations are considered to be the group of first order differential equations which are the derivatives of the state variables, and the number of state variable is always equal to the order of the system. For example, if I consider the order to be 2, then we are going to have two state variables. If the order is 3, then we are going to consider 3 state variables. So both state and output equation should be made as a function of state variable and input. And state model of the system could be written in various forms like physical variable form, canonical variable form and physical variable form. So coming to state variable models, so we are going to consider a model with an example like this, wherein I have considered a input signal u1, u2 and the output signal to be y1 and y2. So input is considered to be a unit step input u of t and the output is considered to be y of t, and the initial condition is taken to be x of 0. For a dynamic system, the state equation is described with the variable, that is state variables, as x1, x2, x3 etc. up to xn, which is shown like this. So coming to state equation, so a state equation is taken as a derivative of the state variable which is defined as y here. So nth order differential equation is generally defined as yn plus a1 yn minus 1 plus a2 yn minus 2 etc. up to an y is equal to u, where u is considered to be your input. And now we are going to choose the state variables like this. The first state variable x1 is taken as y, x2 is taken as y dash, that is dy by dt, x3 is taken as y double dash, that is d square x by dt square, and so on like this. We are going to define this as equal to y to the power n minus 1. So in turn, what you can define here is, since x2 is a derivative of x1, so what I can do is, in the state space equation I can just represent them as x1 is equal to y, x2 is equal x2, which is nothing but equal to y dash is equal to x2, and x2 dash is nothing but equal to y double dash, which is nothing but equal to y3, and so on like this. So you can correlate that xn dash is nothing but equal to yn. So here circle indicates that it is derivative, okay, and you can consider your state equation from this as equal to xn dash is equal to yn, which is equal to minus a1 x1 minus a2 xn minus 1 etc. up to minus an x1 plus u. So this is the state variable equation that we can have for n such variables, standardized form. So all this set of equations what we are going to get can be written in the form of a matrix, which is called a state matrix, or it's also called a state vector. So here the derivative of your x is taken as one matrix, that is d by dt of x1, x2, etc. up to xn. The coefficients are considered to be a11, a12, etc. up to a1n, and till ann you can have this matrix, that is coefficient matrix, and this is your state vector matrix with a variable as x1, x2, x3, etc. up to xn. So with the coefficients of b and the input u. So the column matrix consisting of the state variables x1, x2, x3 is considered as your state vector. This is considered to be our state vector, which has the variables x1, x2, x3, which are nothing but our state variables. So the vector of the input signal is defined as u. The system can be represented by the compact notation of the state differential equation as x dash is equal to ax, where a is your coefficient matrix for a and b is the coefficient matrix of b coefficient. X is your state variable matrix and u is your other matrix that we have. So the differential equation is commonly called as state equation. This particular equation is called as state equation, where A is an n cross n square matrix, B is an n cross m state matrix, and the state differential equation relates the rate of change of state of the system to the state of the system and the state of the input signal. In general, the outputs of a linear system can be related to the state variable and the input signal by an equation as y is equal to cx plus du, where y is considered as set output signal expressed in column vector form, and the state space representation is comprised of state variable differential equations and the output equations. So these two equations you must remember. Now coming to state space modeling, if vector functions f and g do not involve time t explicitly, then the system is called as time invariant. So it is not depending upon the time. In this case, the state and the output equations can be simplified to x dash of t equal to ax of t plus b u of t, and y of t can be considered as is equal to c into x of t plus d into u of t. Similarly, you can write the state model for this by considering u. So these two equations are represented in the block diagram form, which is as shown here. And this is an example which I am taking to write the state model. So here a mechanical system is given with a mass m, dashpot B, spring key, and u of t is the force applied and y of t is considered to be the output here. And now if we write the system equation for this, I am going to get my equation as m y double dash of t plus b y dash of t plus k into y of t as equal to u of t, which is our input. So here I am going to consider the two state variables, that is x1 and x2, because the order here is y double dash, so it is a second order system. So I am going to consider two variables, that is x1 and x2. x1 is taken as y of t and x2 is taken as y dash of t. Now we will see how to represent this using the state equation. So x1 of t is taken as y of t, x2 is taken as y dash of t, and your this is our equation that we have for the mechanical system. Now if I represent the state equation for this, x1 dash of t is nothing but equal to x2 and x2 dash of t is nothing but equal to, by separating and rearranging the terms, we are going to get the value as minus b by y dash of t, minus k by m y of t plus 1 by m u of t. So these two are our state equations, and now x1 dash of t is taken as equal to x2 of t. So this is our equation, and this is our second equation that we are going to replace by replacing y1 dash of t with x2 and y of t with x1. So now the variables can be combined and it can be written. We are going to consider the output equation to be as y of t equal to x1 of t. So similarly, if we rearrange and if we construct the matrix, I am going to get the state vector matrix as equal to x1 dash of t, x2 dash of t is equal to 0, 1, minus k by m minus b by m into x1, x2 plus 0, 1 by m into u of t. So this is now in the standard state equation form, and y of t can be written as equal to 1, 0, x1 of t into x2 of t. that is, it is equal to x1, right? So in our state vector table we have x1 and x2. So for x1 I have put 1 and for x2 we have taken it as equal to 0. This is how the state matrix can be constructed for a given block diagram. So state diagram for this system can be drawn using the relationship like this. So first we are taking the input u of t, okay. So then we are writing the values minus b by m, because it is the delay here is taken to be 1 by s and then 1 by s. We are constructing, so this value is taken as minus k by m because this is x1. So this is 1 by m because we are taking u of t here, y of t is our output, and this is x2 which is equal to x dash. Okay, so it's taken, we are writing the system by using the Laplace representation. That is why derivation here is represented in with integration as 1 by s. So another example is given here, wherein you need to write the state model for the given differential equation, which is taken as y triple dash plus 3y double dash plus 2y dash is equal to r of t. Now x1 is taken as equal to y, x2 is taken as equal to y dash, and x3 is taken as equal to y double dash. So in turn we are going to write x1 dash as equal to y of 0, which is equal to x2, x2 dash as equal to y double dash, which is equal to x3, x3 dash is nothing but equal to y triple dash, which is equal to minus 3y double dash minus 2y dash minus y plus r of t. So if we write this above equation in the matrix form, we are going to have the equation as x1 dash, x2 dash, x3 dash equal to 0, 1, 0, 0, 0, 1, 1 minus 2 minus 3, x1, x2, x3. And if you have only one input, so r of t, so it is 0, 0, 1. In the third equation, we have r of t, so it is 0, 0, 1. And output equation is nothing but equal to x1 itself, so y is equal to 1, 0, 0, x1, x2, x3. So this is our output equation for the set of values that we have. So this is another example which is given here. You need to convert the transfer function to a state model. So transfer function is given. First thing is you are supposed to cross multiply your values and take inverse Laplace transform and convert it into time domain. So by converting it into time domain, we are getting the values y triple dash of t plus 9y dash of t plus 26y dash of t plus 24y of t equal to 24u of t. For this we are supposed to write the state model. So now as usual we are going to choose the state variables. So y triple dash is taken as x3, y double dash is taken as x2, and y dash is taken as equal to x2, and x1 is taken as equal to y of t. So x2 dash of t is nothing but equal to x2 of t, x2 dash of t is nothing but equal to x3. So by considering the equation and by solving for x3 of dash, we are going to get the state model equation as x1 dash of t plus x2 dash of t plus x3 dash of t equal to 0, 1, 0, 0, 0, 1 minus 24, 26, 29 x1, x2, x3 plus 0, 0, 24 u of t. And the output equation is just equal to y1 equal to x1 of t. So it is directly taken as 1, 0, 0 x1, x2, x3. Like this you can try few more examples. So this is a small content of 5th module which we have discussed. So in today's session you have learned about definition of state space, state variable, state vector matrix, and how to construct the state vector matrix for a given set of variables or for a given block diagram is learned. So usually the questions will appear on definitions of state variable, state vector matrix and so on. So you just need to pay concentration on that. And along with that we have solved 2 or 3 examples wherein we have learned how to construct your state equations. So this is a brief overview of state space analysis. I hope you have followed and the session was interesting. Thank you all for joining the session. Have a nice day.